This is the first year algebra-based physics course. Topic 2 is one-dimensional kinematics. In this section, 2.12b, I'll be continuing to speak about free fall. Some vocabulary. Gravitational force. The pull experienced by an object, or any mass for that matter, as a result of the mutual attraction between it and another mass. Weight. The gravitational force experienced by an object, or any mass, located on or above the surface of a celestial body. Acceleration due to gravity is the rate of acceleration that an object experiences in free fall above the surface of a celestial body. And what free fall is the condition in which the only force acting on an object is its own weight, symbolized Fg. So what is a gravitational force? Well, all masses attract each other. It doesn't matter whether the mass is solid, liquid, or gas. They all attract each other. A force can be a push or a pull. In this case, we'll be talking about forces that are pulling. A force or pull that one mass exerts on another as a result of their mutual attractions is a gravitational force. So what we mean is that if you have, for example, two apples and you put them near each other in outer space, this apple is going to attract this apple, and this apple is going to attract this apple. They have a mutual attraction. They're going to be attracted toward each other. Now, the symbol for gravitational force is Fg. Watch. Gravitational force. Gravitational force. That's actually a capital letter F and a subscript, a very small little g. The unit for all forces is the Newton. Now, you want to label the forces Fg. When we get into the forces topic, we'll make one of these Fg's negative. For now, we'll just say they're both gravitational forces. So what do we usually mean when we say an object's weight? When we speak of the gravitational force, which is a celestial body. Now, a celestial body could be a planet, a star, a comet, an asteroid, right? Any relatively large object floating out there in outer space. A moon. Here in the 21st century, we should probably also include space stations, which generate artificial gravity. So, when we speak of the gravitational force, which a celestial body exerts on an object at or above its surface, we call this Fg, the object's weight. So here we have the Earth. Here we have an apple that is either held above the surface, or it could be falling down to the surface of the Earth. It doesn't really matter. The Earth is exerting a force downward on the object. The object is exerting a force upward on the Earth. We're focused on the gravitational force that the Earth is exerting on the object. And we could symbolize that Fg, and that would be a gravitational force known as the object's weight. The apple's weight. All right, so we're focused on this gravitational force. We're not really too concerned, if we're talking about the object and the object's weight, we're not terribly concerned about the force that the apple exerts upward on the Earth. It's pretty tiny, pretty negligible. You see, even though these two forces are the same magnitude, you put this force on an apple, the apple's going to fall down pretty fast. You put the same force on the Earth, which is much, much more massive, it's really not going to affect the Earth very much. Acceleration due to gravity. The rate at which an object accelerates toward the center of a celestial body. Synonym would be free fall acceleration. the symbol would be g or a. A, it's a type of acceleration. The unit, it's a type of acceleration. The unit has to be meters per second squared. Meters per second squared. So now, why do objects accelerate towards celestial bodies? The gravitational force, which is celestial body, let's look at the Earth, the Moon, and Jupiter. All right? The gravitational force, which is celestial body, pulls the objects in free fall down toward their centers, causes them to accelerate at a constant rate. Now, what's the rate for the Earth? You know that the rate at which objects accelerate toward the surface of the Earth is 9.81 meters per second squared. Most of the time we round that up to 10.0 meters per second squared. The acceleration due to gravity on the Moon is approximately 1/6 of the acceleration due to gravity for the Earth. So take 9.81, divide it by 6, 1.62 meters per second squared is the approximate acceleration due to gravity on the Moon. For Jupiter, the acceleration due to gravity is much, much larger, 25.9 meters per second squared, approximately. This means that objects will fall to the ground faster on Jupiter, slower on the Moon, compared to the Earth. Could you imagine dropping an object on Earth and it falls down, bam, right? But if you drop that same object on the Moon, it doesn't go down as quickly. That's crazy. With this diagram, we'll show that both Fg on the apple and g, or a, the acceleration due to gravity that the apple experiences, are small for the Moon, bigger for Earth, and largest of all for Jupiter. Now keep in mind, these diagrams are absolutely not to scale. All we know is that the Moon has the smallest, Earth is in the middle, and Jupiter has the largest. Now, we know that the Earth exerts a downward pull on the apple. I'm going to put it slightly off center. Fg. The Earth exerts a gravitational force on the apple. The Moon exerts a gravitational force on this apple. But this gravitational force is smaller than the one that the Earth exerts on the apple. Jupiter exerts a downward pull, a gravitational force on this apple. And we know that this gravitational force is larger. It's a larger magnitude than that which is on the Earth. On the apple that is near the Earth. Now, these are the gravitational forces. Right? The smallest here on the same apple, the smallest gravitational force would be when you put the apple near the Moon. A medium gravitational force would be when you put the apple near the Earth. And the strongest or largest gravitational force on this same apple would be when you put the apple near Jupiter. Now assume, of course, that we're putting the apple the same distance above the surface of each planet. Now, those gravitational forces cause an acceleration. They cause the apple to accelerate. Now, of course, acceleration is another vector. I'm going to draw the acceleration with a thin blue line. All right, so here's the acceleration that the apple experiences. On the Moon, the apple would not experience it as great an acceleration as it does on the Earth. The same apple above the surface of Jupiter experiences the greatest or largest acceleration due to gravity. And again, you can abbreviate acceleration due to gravity either A or G. A or G. A or G. All right, now of course, we should label this Fg Earth and this A Earth. This one on the same page would have to be labeled Fg Moon, A Moon, Fg Jupiter, A Jupiter. All right, these numbers are not going to be the same. You can tell from the relative sizes of the vectors. Now, Both force and acceleration are both vectors. The force is causing the acceleration, but they are not the same vector. The symbol for force in this case is Fg. The symbol for acceleration is lowercase a. The unit for force would be the Newton. The unit for acceleration, you know, is the meter per second squared. So, bottom line, the acceleration on the moon is the smallest. The acceleration due to gravity for the Earth is in between. And the acceleration due to gravity for Jupiter is the largest. We can put those numbers in one more time. For the Earth, we said that G, all right, this for the Earth is 9.81 meters per second squared. For the moon, and you can look these up on the internet, no problem. For the moon, the acceleration due to gravity would be 1.62 meters per second squared. And for Jupiter, the acceleration due to gravity for Jupiter would be 25.9 meters per second squared. Right, so when we do calculations, you have to know what planet you're talking about, because G changes. So what is free fall? We stated earlier that free fall occurs when the only force acting on an object is a gravitational force caused by a celestial body. In other words, the only force acting on an object is its weight. So, some examples of free fall that we're going to take a more careful look at in this lesson. The first example would be an object that is falling straight down. It doesn't matter whether you drop it from rest or you throw it down. It's still going straight down, and it is in free fall. After you let go of it, it is in free fall. Another example, an object that is thrown straight up. Take, for example, this apple that just appeared out of nowhere. If you throw the apple straight up, what happens is it rises to a maximum height, stops briefly, and then falls straight back down. We'll be looking at examples like that also. Another example would be an object that has a horizontal velocity. Now, don't try this at home, but if you had a high cliff and a car were to drive off the cliff, definitely don't try this at home, then after the car leaves the ground and is flying through the air in an arc down to the ground, that car would be in free fall. After it leaves the cliff, that car would be in free fall. Now, the final example would be an object that is thrown upward at an angle. Like, for example, a football. A quarterback is passing a football to a receiver on the other end of the field. So the quarterback throws it upwards at an angle. The ball arcs upward, rises to a maximum vertical height, and then starts arcing back down again. After the football leaves the quarterback's hand, and before it's in the hands of the receiver, while the football is in the air, the football is in free fall. So we're going to take a quick look at these examples. So we're going to take a quick look at these examples of objects in free fall. And of course there are billions of other examples, but we'll start with these four. A quick little reminder for free fall, for kinematics. Does the mass of an object affect how fast it falls? What do you think? The answer is no. Wait a minute. You don't like that? All right, ask it a different way. Try this. Do heavier objects or more massive objects fall faster than light objects? What do you think? The answer is no. Still don't like that answer, huh? Okay. Let's ask the question a different way, see if we get a different answer. Let's try this. If we drop a marble and a bowling ball together, which one hits the ground first? Answer? Neither. Neither. Absolutely. They hit the ground at the same time. They hit the ground at the same time. So no matter how you think about it or how you ask it, when you drop two objects, I don't care how big one is and how little the other one is, they hit the ground at the same time. Keep this in mind for all of kinematics. The most important thing, what we're talking about here, is that for all of the kinematics topic, one-dimensional kinematics and two-dimensional kinematics, we're not really going to mention mass too much. We're not going to take the amount of kilograms and put it into the equation. We'll start doing that in the forces topic, where it starts to be a factor in our calculations. Right? So the mass of the objects does not matter in the kinematics topic. Now, a quick and easy way to remember how objects accelerate on Earth is to use the magic chart. You should memorize how to construct the magic chart and how to use the magic chart, what the numbers are for, let's say, the first 6 seconds of an object's fall. 2 rules for starters. Now, you can bend these rules a little as you get better at this, but 2 rules just to get started. The object must start from rest, and these numbers are for Earth. Right? Keep those 2 rules in mind. So, the magic chart. We've got a chart with 3 columns. The first column would be time in seconds. The next column would be distance in meters. You can think of it as displacement. And the last column would be velocity in meters per second. Right now, everything starts at 0, time 0, distance is 0, velocity is 0. Remember, the object starts from rest, so the initial velocity here is 0. Right now, time can be 1 second later, 2 seconds later, 3 seconds later, 4 seconds later, 5 seconds later, or 6 seconds later. All right? Now, let's figure out that the distance an object falls from rest in 1 second. So here's the equation. All right? D equals V initial t plus 1/2 at squared. We know that V initial is 0, so we get rid of that. So D equals 1/2 at squared. We know that the acceleration due to gravity on Earth is 10 meters per second squared, so 1/2 of 10 meters per second squared is going to be 5, and then t squared. So in this column, you're going to calculate 5t squared for this t, for this t, for this t. All right, 1 second after you drop the object, 2 seconds after you drop the object, 3 seconds after you drop the object, etc. Remember, it doesn't matter what the object is. It can be a mouse, an elephant, a marble, or a bowling ball. They're going to fall at the same rate. They're going to hit the ground at the same time. They will have the same velocities at the same times after they were released. So here we put D equals 5t squared. All right, at time 1 second, that's 5 meters down. After 2 seconds, 2 is the time, squared is 4 times 5 is 20 meters down. 3 is the time, squared is 9 times 5 is 45 meters down. 4 squared is 16 times 5 is 80 meters down. 5 seconds after you drop the object, how far down is it? 5 is the time, squared is 25 times 5 is 125 meters down. And finally, 6 seconds after you release the object, 6 squared is 36 times 5 is 180 meters down. Okay, so it's very easy to fill in this column, but you really should just memorize this column, this column. Now here we go with the velocity. How fast is the object going after it's been falling for 2 seconds? After it's been falling for 3 seconds? After it's been falling for 5 seconds? How fast is it going? What's the final velocity? V final equals V initial plus AT. We know that the initial velocity was 0. Goodbye. Acceleration times time. We know that the acceleration is 10 meters per second squared times the time. All right? So we know that ultimately this last column here is going to be 10 times the time. So V final is going to be 10 times the time. All right, let's make a fancy T there also. Okay. All right, so after 1 second, how fast is the object falling? It's falling at 10 meters per second. Of course, we've got the unit up there. We don't have to keep copying the unit. After 2 seconds, it's falling at 20 meters per second down. You know it goes faster and faster as it goes down. And you know, by the way, that an acceleration of 10 meters per second means that the speed changes 10 meters per second every second. So after another second, it's 30 meters per second. After another second, it's 40 meters per second. After 5 seconds, it's 50 meters per second. And after 6 seconds, it's 60 meters per second. Memorize how we got these numbers and then memorize the numbers. All right, this will help you. And again, this is only for Earth. You cannot use these numbers if we drop an apple on the moon or on Jupiter. Let's look at the example where an object is dropped from rest, from a specific height. In this case, an apple is dropped from a height of 45 meters. So in other words, from where the apple is let go down to the ground, right, is 45 meters. I'll call it dy because it's vertical. 45 meters high. All right? So this is the maximum height that we're looking at here. Now, we know that the apple experiences a force downward. All right, I'm going to offset this arrow slightly from center because we'll also be drawing in the acceleration of the apple. All right, so the apple experiences a force, Fg. All right, the apple experiences a force all the way down, Fg. All right? And the apple also experiences an acceleration. We know that the acceleration on the Earth, I'll make that a thin blue line, all right, G or A, we know that that's 10.0 meters per second squared. All right, we'll round off the 9.81 to 10 meters per second squared. All right, so when we first let the apple go, there's a force on the apple, and the apple experiences an acceleration. As the apple falls down, there's a force on the apple, and the apple experiences an acceleration. All right, now let's take a look at what we know based upon the magic chart. Now you should have a copy of the magic chart nearby. If necessary, go back in the video and make a copy of the magic chart, whether you take a screenshot or copy it down onto a piece of paper. I'd have a copy of the magic chart on available, and at some point you're going to get that magic chart memorized in your head. All right, now, the initial velocity was 0 meters per second. We know that the acceleration is 10 meters per second squared. We know that dy, or the maximum height, all right, we call it dy here, right, or d max, all right, is 45 meters. So what we'd like to know is what is the speed when the apple hits the ground, and how long does it take? How much time does it take? Well, from the magic chart, and I'll put in a quick little magic chart here, T, D, V final. All right, 0, 1, 2, 3, 4, 5. All right, 0, 0. This is 5. This is 20. This is 45. 80, 125. This is 10. This is 20, 30, 40, 50. All right, we know to fall 45 meters, it's going to take 3 seconds. All right, and the speed when the apple hits the ground is going to be 30 meters per second. All right? Now, just keep in mind that technically, all right, the acceleration is negative. When the apple hits the ground, it's falling down, so the speed is negative, or I should say the velocity is negative. And the displacement, if up here is considered 0, down here would be negative 45. All right, you can think of it that way also. All right, but in any case, it's very easy from the magic chart to figure out that falling 45 meters, I don't care what the object is, it's going to hit at a speed of 30 meters per second. The acceleration all the way down is 10 meters per second squared. It takes 3 seconds to get to the bottom of a 45-meter cliff or building. This time, we have a situation where an object is thrown straight up with an initial velocity of 20 meters per second. Now, I'm not going to do that here. I'm not going to throw it up with an initial velocity of 20 meters per second, but we're going to make believe. All right, so thrown straight up, all right, it stops briefly at maximum height. In other words, it stops here and then falls straight back down. All right, so this is a situation where once I let go of the ball and it's not in my hand anymore, right? And in the worksheet, this is a basketball. All right, but once I let go of it and it's not in my hand, it is in free fall the entire time until it's back touching my hand again. So I let go of it, free fall, free fall, free fall, free fall. It's free fall all the way up. It's free fall when it stops at the top, and it's free fall all the way back down again. All right, so the entire time that it is not touching my hand, the ball is in free fall. All right, all the way up, all the way back down. All right, so let's take a look at what's happening here. All right, now, in the worksheet, or I should say in reality, all right, from here, we'll make this, we'll put my hand down here. This is going to be the worst hand you've ever seen drawn. Here's my hand. Oh, my goodness. Okay. Here's my hand. Okay. Now, the ball leaves my hand, all right, and all the way up, stops here briefly, and then all the way back down. So it's straight up, straight down. So technically, the ball starts here, goes straight up, stops here, and then straight back down. Now, what I'm going to do in the worksheet is just offset the trajectory just a little bit. Instead of going straight up and straight down, I'm going to draw it kind of like this. All right, so it's easier to label things. All right. So, all right, here, this will be my hand down here. All right. And so the ball goes up, 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 and then comes back down. All right, down, down. All right. Now, the whole time, there is a gravitational force on the ball here. That is the only force on the ball as long as it's not touching my hand. So that is your Fg. All right, Fg, the same Fg. All right, the same Fg. Notice I'm trying to draw them all the same magnitude, the same length. All right, the same Fg. All right, and the same Fg. So the Earth is pulling the ball, pulling the ball, pulling the ball. All right. Now, the entire time, the ball is accelerating. I'm going to draw the acceleration as a thin blue line. All right, that's A or G. We know that it's 10 meters per second squared. A or G, A or G. The acceleration is straight down. The force on the ball, now remember, Fg, the force on the ball is the gravitational force that the Earth is exerting on the ball. You can call it the ball's weight. All right? Now, we know that the initial velocity here, when I launch it upwards, is positive 20 meters per second. All right, positive 20 meters per second. We know that at the top here, it stops. So the velocity here is 0 meters per second. Now, when the ball gets back down and slams onto my hand, we know that the velocity here is negative 20 meters per second. It hits my hand. Right, if it started at 20, then coming back down, it's 20. But here it's going up, it's positive. Here it's coming down, it's negative. What we want to look at now is the initial velocity to the final velocity, that time frame from here to here. Now again, keep in mind that this doesn't really slide over like this. We're going straight up and coming straight back down. Right? Technically straight up, straight back down. From my hand, straight up, straight back down. Right? Straight up, straight back down. Okay? Now, your final velocity is negative 20 meters per second. If I were to throw this ball up at positive 5, when it comes back and hits my hand, it hits at negative 5 meters per second. If I were to throw it up really fast, whoosh, right? Yeah, oh yeah, it's great. Whoosh, right, there it goes. All right, straight up, straight back down. I threw it up really, really fast. Let's say it's 40 meters per second. It's not, but let's just say it is. If I throw it up at positive 40 meters per second, when it comes back down, hits my hand, the velocity is negative 40 meters per second. All right, so up at positive 20, down at negative 20 meters per second. The acceleration the whole time is negative 10 meters per second squared. I'm putting the negative there because I'm making a distinction between up, positive 20, and down, negative 20. Now, according to the magic chart, all right, let's figure out the amount of time, all right, and let's not do d max, let's do the total displacement. So in other words, from start to end, what was the displacement? Well, if it starts here and ends here in the same spot, the displacement is 0. All right, so if I start at positive 20, it goes all the way up, comes all the way back down, negative 20. The displacement is 0. From start to end, it hasn't gone anywhere. All right, now, let's do the magic chart. Okay, let's call this the displacement. And let's also do the distance. Let's do the total distance. All right, that the ball traveled. All right. Let's do that also. Let's distinguish between distance and displacement. All right, remember your magic chart for figuring out the time, all right, and the displacement, the distance here. All right, time in seconds. All right, distance in meters. Final velocity in meters per second. 0, 1, 2, 3, 4, 5. That'll be enough. 0, 0. This is 5. This is 20. 45, 80, 125. Speed 10, 20, 30, 40, 50. All right, now, you remember me saying that the initial velocity has to be 0. Well, you can bend that a little bit. All right, if we start at an initial velocity of positive 20, right here, 20, we can go backwards. All right, if we start with an initial velocity here of 20 and go to here, 0, a speed of 0, right, how long is that going to take? That's going to take 2 seconds. How high is it going to go? It's going to go up 20 meters. All right, so you see that the time to go just up is 2 seconds. Now the time to come back down again from 0 back to 20 again, all right, whether this is positive 20 or negative 20, the time to come back down again is another 2 seconds. So what amount of time did the entire trip take? All the way up, all the way back down. How much time did that take? 2 seconds up, 2 seconds down. The total time here is 4 seconds. You see how much you can do with the magic chart, how versatile the magic chart really is. Now, what about the distance? Well, it was 20 meters up plus another 20 meters back down. The total distance that was covered by the basketball, all right, remember in the worksheets it's a basketball, the total distance that was covered is 40 meters. All right, so you can figure out this entire free fall problem by using the magic chart. Okay, so again, we said that V initial was positive 20. It stops briefly up here, that's 0. 20, speed of 20 to a speed of 0 takes 2 seconds. How much distance does it cover? 20 meters. Then to come back down again from 0 back to 20, from 0 back to 20 is another 2 seconds, covered another 20 meters. So if the initial velocity here is positive 20, we want to think what happens when we get to the final velocity of negative 20. We'll go from here, right, from here, up, back down, from here to there, back to the same spot. The acceleration, 10 meters per second squared, does not change. The total time up and down, 4 seconds. The displacement, well, start to end, same place. The displacement is 0. The distance covered is 20 plus 20. The distance covered is 40 meters. Now, I want to show you 2 other ways to look at the same action. Right? Up, back, down. There are 2 other ways to analyze that action. Instead of going from all the way from the beginning, all the way to the end, there are 2 other ways to look at this situation. Let's do that. So here we go. Same ball or basketball thrown straight up with an initial velocity of 20 meters per second, stops briefly at maximum height, and goes straight back down. Now, what we're going to do this time is instead of analyzing the entire procedure, right, from beginning to end, we're going to look at just up. Right, so the object starts here with an initial velocity of positive 20. So the object starts here with an initial velocity, v initial, of positive 20 meters per second. And if we look at just up, then v final up here is where it stops briefly, and v final would be 0 meters per second. So v initial on the up only is positive 20 meters per second. V final is 0 meters per second. Now, if we take a look at the magic chart, and I think we're going to put it right here. All right, we take a look at the magic chart, time, distance, v final, 0, 0, 0. 1, 2, 3 will do it. Okay, actually 2 will be enough, but let's see. We got 5, 20, 45. That's 10. That's 20. That's 30. All right, so if we start at a velocity of 20 meters per second right here, okay, and we go to 0 from here to here, that's going to take 2 seconds. So to get from here to here takes 2 seconds. We know that the acceleration, right, is negative 10 meters per second squared. We know that. Now, the displacement from here to here, right, if this is 0, then this would be positive 20. Now, how do we know that? To go from 20 to 0 takes 2 seconds. How much distance does it cover? 20 meters. So if this is 0, this would be 20 meters. All right, it's a coincidence that the velocity is 20 and the distance is 20. All right, so the displacement is positive 20 meters. The distance covered is 20 meters. That's just on the way up. Start here, end here. Now, what about just on the way down? Starting here, v initial is 0. And when it hits down here, well, if it started at positive 20, here's the ball again. Right, if it started at positive 20, when it hits, it's negative 20. So v final here is negative 20 meters per second. So let's look at down only. V initial is 0 meters per second. V final is negative 20 meters per second. Excuse me. The acceleration is negative 10 meters per second squared. How much time does it take to go from v initial 0 to 20 meters per second? From 0 to 20 takes 2 seconds. So the time to go just down is 2 seconds. The displacement, if this is 0, then down here would be a displacement of negative 20. Negative 20 meters. And the distance covered is 20 meters. Because with distance, we don't care about direction. All right, so what we did here was the first time that we looked at this situation, we said that this was V initial and bam, that was V final. The second time we looked at this, we said that this was V initial and up here is V final. All right, V initial, V final. Okay, now the third time that we looked at the same situation, we only looked at down. This was where we started, and we only looked from here down to there. So you see, you can look at the entire situation up, down, or you can look at just up, or you can look at just down. All right? I would go over this one more time. It's a little tricky, but it'll be very, very simple once you get the hang of it. Here we have a situation where an object is projected horizontally from some height, and the object falls to the ground following a half-arc path. So what we have here is a car. We have a cliff, right, like a high mountain. We have a cliff. Here's the ground. The height of the cliff is 80 meters. The height of this cliff is 80 meters. All right, so actually, we know the distance right now. All right, the height of the cliff is 80 meters. We know the distance. And we know the displacement also. We'll write that down in just a minute. Now, so the car drives that way off the cliff. And obviously, the car starts falling down like this. I'll give you a red. The path of the car is red. All right, so there's the path. The trajectory, if you will. All right, now, this is just before the car hits the ground. Now, since the car is not in free fall here, I'm not going to label any of the forces on the car. Here the car is in free fall, here the car is in free fall, and right before it hits the ground, the car is in free fall. You've got your gravitational force, or the weight of the car, straight down, the weight of the car straight down, the weight of the car straight down, Fg. All right, the weight of the car is always straight down. Now, the car is accelerating downward. It's falling faster and faster downward. The acceleration due to gravity of the Earth, all right, A or G, all right, 10 meters per second squared. Okay? We've got A or G is 10 meters per second squared. All right, we've got A or G is 10 meters per second squared. All right, now, we want to figure out as much as we can about the up to down motion of the car. I don't care about anything that's happening across. We're looking at the up to down motion of the car. Now, the car starts from this height. So this is 0 meters. So down there would be a displacement of negative 80 meters. So we know that the displacement is negative 80 meters. Let's take a look at the magic chart to help us out. Time, distance and displacement, speed or velocity, zeros, 1, 2, 3, 4, 5. That should be enough. It's 80 meters. All right, in 1 second it falls down 5 meters. In 2 seconds it falls down 20. In 3 seconds, objects fall down 45 meters. In 4 seconds, objects fall down 80 meters. That's all we need, right? Don't need the 5 seconds. All right, 10, 20, 30, 40. All right, so we're looking at 80 meters right here. Okay, now, the initial velocity, if the car drives off the cliff that way, the initial velocity down is 0. It's not going down until it gets off the cliff. All right, so the initial velocity down is 0. All right, now the final velocity down here, 80 meters down, after falling for 80 meters, the final velocity of the car is 40, or you could say negative 40, because we know it's falling down. The acceleration due to gravity, we know, is negative 10 meters per second squared. How many seconds did it take the car to hit the ground? Well, to fall from a height of 80 meters, how many seconds does it take to hit the ground? It takes 4 seconds. It takes that car 4 seconds to hit the ground. All right, so this is another example of free fall. The car is not in free fall here, but once it's not touching the cliff anymore, once it's just in the air, whether it's going up or down or going across and down, whatever, free fall, all right, free fall, free fall, free fall, free fall, free fall, free fall, just before it hits the ground, free fall. Another example of free fall. For our last example of free fall, an object is thrown in a complete arc from one place to another. In this case, a football is thrown in a complete arc from the quarterback to the receiver. Let's see what we've got here. In order for the quarterback to effectively throw the football to the receiver, here's the quarterback, Q, here's the receiver, R. The quarterback should probably throw the football at an angle. He should probably throw the football something like this, that direction. Now, obviously, if he throws it that way, he's partly throwing the football to the right, and he's partly throwing the football up. That throw at that angle is partly to the right and partly up. So what we have here is we can break the initial velocity up into an initial to the right velocity and an initial up velocity. Now, what I'd like to talk about is a situation where the initial velocity upward is 10 meters per second. All right, so the initial velocity upward of this football, I'll put it right there, the initial velocity upward is 10 meters per second. All right, the initial velocity is, let's say, positive 10 meters per second. All right, now, for this problem, we're only going to go to the halfway mark. All right, for the most part, we'll only go to the halfway mark. I'll talk briefly about what happens if you go all the way. All right, but to the halfway mark, all right. Now, in the beginning, the football has an initial velocity upward. When it gets to here, does it go up anymore? No. Why not? Because the upward velocity here is 0. It's not going up anymore. At this point, right here, halfway, right through this procedure, the final velocity is 0. This is the final velocity in the up and down direction. I don't care about a cross. Forget about a cross. We'll do a cross in later videos. Now, we know the acceleration up and down is negative 10 meters per second squared. Now, if the initial velocity is 10, right here, how long does it take the ball to get to here? To get to where the final velocity is 0? It takes 1 second. So the half time, the amount of time to get halfway to the receiver here, is 1 second. That means that the full time to here would be 2 seconds. It would take 2 seconds to get to the receiver. If it takes 1 second to get to here, it takes 2 seconds from here to here. All right, now, maximum height. Well, if the initial velocity was 10 and the final velocity is 0, 10 to 0, how far does the ball go? What's the distance the ball travels in that time? 5 meters. The height up. The height in the vertical direction. Forget about horizontal. The height in the vertical direction is 5 meters. All right, so again, this is an example of free fall. the football, all right, here's the football, has the only force on it is Fg, all right, Fg, remember, Fg is straight down, straight down, straight down. And the acceleration of the ball downward is 10 meters per second squared, 10 meters per second squared, 10 meters per second squared, 10 meters per second squared. So the ball has two vectors. It has a force straight down. It has an acceleration straight down. There's also a velocity vector. We're not drawing that at this time. All right? So we figured this out using the magic chart. Now, we really only needed to go up to there. We didn't need all this. All right? We only needed to go up to 10 because the initial velocity upwards here was 10. All right? Let me just close that off. Okay, so we've done an introduction to several circumstances that are examples of free fall. Taking an object, dropping it straight down, boom. All right, as long as it's not touching my hand, it's in free fall. Second example, taking an object, all right, launching it straight up, comes straight back down. The time when it's not touching my hand, it is in free fall. Take this apple, and I don't want to ruin the apple. Take the apple, and the apple goes off. The apple runs off a cliff. Maybe we better use a car. The apple runs off a cliff and goes down in a half arc. As long as it's not on the cliff or on the ground, the object is in free fall. And finally, the situation where we launch an object at an angle. Maybe I should use my left hand because I can catch better with my right. The object goes up at an angle, all right? And as long as it's not touching either one of my hands, it is in free fall. All right? And you can use the magic chart, all right, to analyze. Whoop, there goes my apple. You can use the magic chart to analyze all of these situations. That's a good apple. That's a Honey Crisp. That's a good apple. That's a Honey Crisp. That's my favorite apple. Stay healthy. Eat right. See you in the next video.